The vibrating electric and magnetic fields make light a part of the electromagnetic spectrum. These waves can travel through the emptiness of space as a form of radiation. They travel as invisible transverse waves. Visible light only makes up a very small part of the electromagnetic spectrum. Light travels as waves. Light also behaves like a particle. Because light appears to have the properties of both particles and waves, scientists refer to it as the particle-wave theory of light. Isaac Newton in 1665 made some important discoveries about light and color. He found that white light entering a glass prism could be bent and separated, or refracted, into 7 color groups. These principal color groups were red, orange, yellow, green, blue, indigo, and violet. To remember the order of these colors, think of their first letters to form the name Roy G. Biv. Newton conducted other experiments and found that all 7 refracted colors could be bent again with a second prism back to make white. We call the collection of these 7 colors, of which white light is composed, the visible spectrum. The colors bend at different angles because the colors each travel at different speeds. Violet is bent the most because it travels slower than the other colors when it goes through glass or water. Light travels slower through water and glass than it does through air, so it's easier to see this effect when we use them. Red bends the least because it travels faster than the other colors. All the colors have their own speeds. We don't need a glass prism to break light into its spectrum. In fact, nature can provide us with a beautiful spectrum in the form of a rainbow. Rainbows occur when sunlight is refracted in small droplets of water. The raindrops act like little water prisms that refract the light and form the rainbow. Light is a form of radiation given off by the sun. It is part of the electromagnetic spectrum. Actually, it is a very small part of the spectrum, as you can see in this chart. Humans can only see the section called the visible spectrum. The other forms of radiation are invisible to us, but they are still there. The rays of different types of radiation have different wavelengths, just like the different colors of the spectrum have different wavelengths that cause them to separate into the color spectrum. Radio waves with the longest wavelengths are at the end of the spectrum. All television and radio stations broadcast radio waves. Sounds and pictures are changed to electrical signals, which are transmitted by radio waves over great distances, and then received by a radio or television and converted back to electric current and sounds and pictures. Microwaves are the next set of waves on the electromagnetic spectrum. A microwave oven generates microwaves, which penetrate food and cause the water molecules in the food to vibrate. The vibration of the water molecules causes the temperature of the food to rise. Radar also uses microwaves. For instance, a radar gun used by the police sends out a quick burst of microwaves that reflect off a car and return to the gun. The speed of the car can then be determined. Radar guns have been used by the police since the 1950s. These days, more and more police departments are using laser speed guns called LiDAR guns instead of traditional radar guns. The LiDAR gun, which stands for Light Detection and Ranging Gun, determines the time it takes a burst of infrared light to reach a car and bounce back to the gun's detector. This gives a measurement of the distance between the LiDAR gun and the car. The LiDAR gun does this several hundred times in 1 second, so changes in the distance can be used to determine the speed of the vehicle. 2 more types of radiation given off by the sun that we can't see are ultraviolet and infrared. Infrared is found before the visible spectrum, just before red. Infrared energy is heat energy. You feel infrared energy at the beach when you sit in the sunlight. Infrared waves from the sun are absorbed by your skin. We can't see infrared waves, but there are devices that can be used to detect this energy. Brighter colors indicate areas of higher temperature. Ultraviolet waves are just beyond violet on the electromagnetic spectrum. These rays can be very damaging to the skin and can even cause skin cancer. That's why it's not a good idea to sit out in the sun without a strong sunblock. X-rays are next in the electromagnetic spectrum. They are used in various ways in the medical field. Because the rays penetrate many materials easily, they are used to examine broken bones and to check your teeth. X-rays are not harmful unless you are exposed to too many of them, so patients are usually draped in a lead apron to protect areas of the body not being X-rayed. So visible light is actually only a small portion of the electromagnetic spectrum. There are a lot of energy waves that are beyond our ability to see. That doesn't mean they're not there. Experiments have shown that flowers under ultraviolet light have a totally different appearance than what we see. Bees and other insects probably see these flowers as they appear in the ultraviolet spectrum. Isaac Newton's work helped to explain why things have different colors. When we see a nice red apple, it's because the apple is reflecting red light waves and absorbing all the other colors. The white light that strikes the apple contains all the colors, including red. All the other colors are absorbed, and the red bounces off the apple and enters our eyes. The colors we see are the colors reflected by objects. If we light an object with something other than white light, we will get different results. Here is the nice red apple. If we shine a green light on the apple, it will not appear red. It appears black. This is because the green light has no red in it. The green is absorbed, so the apple looks black because it is reflecting no colors. White objects reflect all the colors, whereas black reflects no colors. It absorbs all the colors of light. We can mix different colors of light to make other colors. There are 3 colors of light that can make the other colors of the spectrum. These colors are called the primary colors of light. They are red, green, and blue. Here is a white paper plate. When we shine red light on it, it appears red. When we shine a green light on it, it looks green. And if we combine the red and green light, it appears yellow. If you look closely at a color television screen, you will see that the entire screen is made up of hundreds of dots arranged in groups of 3. There are tiny red, green, and blue dots that can be used to create all the colors you see on television. Don't confuse the 3 primary colors of light with the 3 primary colors of pigments. Pigments reflect different colors and are used in paints and dyes. Pigments may be combined to form different colors, and often an object contains more than one pigment. Mixing pigments is not the same as mixing the primary colors of light. The primary colors of pigments are red, blue, and yellow. Color photographs are made up of these 3 pigments. If you shine a flashlight across the room, you'll see that the light travels straight. It doesn't bend around corners. You may also notice that the light travels fast, very fast. In fact, light is the fastest thing of which we know. It travels faster than a car, faster than the wind, even faster than a jet plane. Light travels at the incredible speed of 186,000 miles, or 300,000 kilometers per second. That's like traveling from New York to San Francisco